Hello and welcome to Late Night Code. So I'm coming at you with another problem from the Southeast Regional 2022 contest, which took place this last February. This problem is called Restaurant Opening. It's rated at a 1.8 on Caddis, which makes it an easy problem, although slightly more difficult than the problems we've already solved. And I believe it was a Division 2 problem in that contest. So let's jump right in. Restaurant opening. It is said that the three most important factors for determining whether or not a business will be successful are location, location, and location. The incredible cooks preparing cuisine are opening a new restaurant in the international city promoting cooking, and they have hired you to find the optimal location for their restaurant. Now, on a side note, this is something that the setters in these contests love to do. They love to find ways to mix ICPC into the problem. So the incredible cooks preparing cuisine, ICPC, and the international city promoting cooking, ICPC, which is just brilliant. The setter somehow managed to mix in ICPC twice and in the same sentence. So kudos to the setter. It's just a classic thing we'd like to do. Moving on, you decide to model the city as a grid, with each grid square having a specified number of people living in it. The distance between two grid squares, R1C1 and R2C2, is the absolute value of the difference between R1 and C2 plus the absolute value of the difference between C1 and C2. In order to visit the restaurant, each potential customer would incur a cost equal to the minimum distance from the grid square in which they live to the grid square containing the proposed location of the restaurant. The total cost for a given restaurant location is defined as the sum of the costs of everyone living in the city to visit the restaurant. Given the current city layout, compute the minimum total cost if the incredible cooks preparing cuisine select their next restaurant location optimally. Our inputs will consist of a first line that contains in and im, which can go up to a maximum of 50. So they are pretty small. In is the number of rows, im is the number of columns. So that's the description of the 2D matrix. Then we have in lines, each containing im integers, which each have a weight that goes up to 50. It's also quite small, so that's just the matrix itself. And then we have to output a single integer, which is the total cost if the restaurant is selected optimally. Okay. So to kind of summarize what's going on here, basically we are given a grid. The grid is composed of a number of cells. It's an in by im grid. We have to pick a cell, and if we pick a cell, then all of the weight in that grid must coalesce onto that particular cell, which means that it's going to incur a cost. The cost here will be the weight of each cell multiplied by the distance that weight has to travel to reach our selection. And then we just want to find the cell that would minimize that cost. And the distance here is going to be Manhattan distance. Okay, so with that, let's go ahead and jump over to Excalidraw. And let's start to get a kind of better idea of this particular problem with just a quick example. So let's go ahead and open up here. Let's just create for ourselves a very basic matrix. We'll just go ahead and have this one, just to keep things simple. We'll just do a 3x3 here. So I'll just go ahead and draw my very, very rough 3x3. Let's add some values. So we'll do a 1, 2, 3. We'll do a 3, 1, 2, and then we'll do a 2, 3, 1. And we'll just have ones along the diagonals. Every time you do a 3x3 this way, it always becomes a bit patterned, but that's okay. And now let's talk about a selection of this middle square. So let's say we want to select this middle square here. What happens as a consequence of selecting this middle square? Well, the first thing that happens is we now need to compute a cost. So for example, the cost of this middle square is currently 0x because we don't incur cost from the current cell. But then all of the other cells, we're told, will need to move. The weight represents the people in those cells, and they now need to move. And so when they move, they're going to incur a cost. So if we have two people in this northern square or this ordinally adjacent square, they're all going to move, and they're going to incur a cost of that movement, which is currently 1x because it's moving by one row value. And everyone on the left here will also move, incurring a cost of 1x because they're moving one column value. And then same thing on the right, they incur a cost of 1x for that one column. And on the bottom, they're going to incur a cost of 1x because of that row movement. Then for all the diagonally adjacent cells, we're told that, well, they're going to have to move here 2 cells because of Manhattan distance. So that means that they're going to move one column and one row. Let me go ahead and do this a little bit better there. So one column and one row. And this would be true for all of the diagonally adjacent places. Now, of course, into this particular matrix for the center cell, these are the maximum distances we'd have to worry about. But if we choose different cells or if we deal with larger matrices, right? These distances can get a lot longer, but this is effectively the idea. And so now if we want to know the cost of this particular cell, all we have to do is now multiply the weight of each cell by the distance it would have to travel, add them all together, and we have the cost of this particular cell. And we just want to know which cell produces that minimum cost. So that's what we have to work with this particular problem. And the other thing that we should go ahead and quickly note is that we are also told that the dimensions of this are n by m, okay, n by m, where both n and m are less than or equal to 50. And that's really important because it means that the maximum size of this particular matrix is 50 squared cells or 2,500 cells, which really is not that many. It's really not that many. Now, the next thing I want to talk about real quick is just what's a good way to crack into problems to kind of get your first handhold. How do you build a mental model or framework for thinking about them? I have my own approach that I really like. And so I've been kind of trying to figure out a way to give it a mnemonic. And the best one I come up with is called level. So this is the level approach. So this is going to be L, E, I don't know why I put a dot there. L, E, V, E, and L. And so the basics of this approach is essentially 5 beats that you can hit as you're trying to crack into this problem, and that you can also follow as you're trying to iterate towards a best solution. So I really recommend this kind of approach for coding contests, but also technical and whiteboard interviews. This can be a really great way to frame your thinking and your communication about the particular problem. So with L, we have learn the problem. And this is essentially the set of steps that we've already followed through. We either read or listen to the prompt, we summarize it out loud, we come up with a better visual, pictographic, graphical, notative, however you want to say it, a better example to come up with another way to communicate what we understand about the problem and to better form the mental model that we have of the problem. Find the right questions to ask. That's an important part of this, right? Then 2, we need to explain/explore a solution. And so this will typically be some kind of gut instinct for your first time through, which means you'll probably be thinking about greedy or brute force. I tend to always gravitate towards a brute force solution first, but that's okay because while those tend to be worst cases for problems, they also tend to have solutions, which means that you can at least start with something and then work towards what's better. And that's okay, especially for technical, by the way. If you have the misconception that with a technical, you need to have the best solution right away, that is not true. The most important thing is that you explain your decision-making process. And if you start with a brute force solution and you can communicate it well, and then work from that to a best solution, that is an absolute slam dunk. So it's perfectly fine to start here. And effectively, we actually just did that for ourselves, right? So when we talked about selecting the cell and then iterating over the cells, well, if we just did that with all of the other cells and then looked at their costs and took the minimum, would we have a solution? Right? So again, if we applied this approach to every cell to compute every cell's cost and then took the minimum, wouldn't we have a solution? We absolutely would. And that's what gets us into this third step, which is validate/verify the solution. And what that effectively means is, does your solution actually work? Okay? Because if you think it works and it doesn't, that means there's something wrong there in the way that you're thinking about the problem or the way that you understand it. And that means that we didn't do a good enough job in step number 1. Okay? But if we did, then we should have a solution at this point that we know works and we could draft, but maybe it's not the best solution. And that's okay. That's where we get into the next part, which is going to be evaluate the complexity. What are the characteristics of the solution in terms of both performance and memory? And we'll typically start with this from a complexity perspective. And so that's pretty easy to do with this particular problem. So currently we know that it's n by m, where both n and m can go up to 50. So very simply, we could just say that this problem is currently, or we could say that this matrix, is currently a n squared matrix, right? Now, if this is an n squared matrix, what is the cost of computing, or rather, what is the complexity of computing a cost? Well, to compute a cost, you have to look at every cell in the grid. And if there are n squared cells, then the computation of a cost is O of n squared. But then to actually translate that cost into a solution, you'd have to do this for every cell. And how many cells are there? N squared cells. So now we have to look at n squared cells, and for each cell, look at n squared cells, which means that the final complexity is now O of n to the fourth. It is more than quadratic. It's above cubic. And so now that means that our rough number of instructions, or approximate number of instructions, effectively comes out to 2500 squared. Okay, right? So 50 squared squared, 2500 squared. Now, if you're thinking that that's crazy, an n-fourth solution, well, that's actually why this problem is probably listed as easy on Caddis, is because 50 to the fourth, it's really not that big of a number. It's actually 6.25 times 10 to the sixth. It's really not a big number in terms of competitive programming contests. Typically, we begin to worry when we get up into 10 to the ninth. We're not anywhere close to that, right? So we actually probably can solve this with a brute force solution. And if we can, without getting a TLE, which is time limit exceeded, well, we take those, especially in contests, we take those. Now in a technical, you probably would want to go further and actually come up with an improved solution, which, by the way, is something that we will do on this video, on this series. For my next bonus episode, I actually want to improve this to get down to an n squared solution. But that's where step 5 comes in, which is loop. Loop means you go back to the top. Let me go ahead real quick and drag up here. That loop means you go back to the top and you start at the beginning. Now that we have a solution with known characteristics that works, can we think about the problem more deeply in order to explore a new solution, a solution with better characteristics and one that, again, still works, right? And we can continue to do that until we get to a best solution. And for many people, this can be kind of an intimidating process because it almost seems like we have no idea when to stop. But it's actually not true, because the more that you understand about your algorithms, your data structures, the more you are equipped to be able to find that best solution, right? If we study the theory of computing, one of the things that the theory of computing will show us is that there is an ingrained relationship, or an entangled relationship, between problems / algorithms / complexity. So that means that problems have an associated complexity with them. And in addition, algorithms / data structures have an associated complexity with them, which means that if you understand your problem well enough, you could also come up with the best complexity for that problem, the best bucket that you're working towards. And on the other hand, if you're looking for a particular complexity, there's also an associated set of algorithms that you need to be looking at for that complexity. For example, this problem is using a matrix, which is n squared. So fundamentally, it's probably going to be n squared. And I'm saying probably right now because, of course, it still relies on the problem itself. But what we've understood from this problem, the fact that it uses an n by n matrix, the fact that it's asking for things like minimum cost, well, we know that this problem's best solutions are going to fit into the bucket of n squared, right? That's what we're going to be working towards. Now, we're not there right now. We're at n to the fourth, but we know that those are going to fit into n squared. Now, let's just say that hypothetically we had an n to the fourth solution and it was possible that there'd be something better than n squared. We'd be thinking about n log n or n, right? Well, here's the thing, right? Take n log n complexity, which is better than n squared. If you ever wanted to think about n log n complexity, well, there's a bucket of algorithms for that. Most best sorting algorithms fit into the n log n complexity. So if you were thinking about, can I get that complexity, then you should be asking yourself questions like, can sorting help me here? Does sorting help me solve this problem? Okay. So there is an association between the two. And if based on your problem and your understanding of algorithms that you can identify an appropriate complexity and also eliminate better categories of complexity than you have currently, then you can reach a terminal condition, right? In fourth right now, not the best. We can get down to n squared. But once we're down to n squared, very simple questions, right? Can I sort this matrix in order to give me a better solution? No, I cannot. So n log n, probably not going to help us here. Can I represent my matrix using a tree data structure, which has logarithmic properties? No, I cannot, right? There's actually I'm going to put an asterisk there because there are some interesting things that you can do with matrix optimizations, but they actually give you a n to the 2.2, not logarithmic. So, but I'm going to leave that to the side for now. Linear. Is there a way to scan one row or column and get a solution? No, there is not. So that means that if we can get down to n squared, which is what we already believe to be the best category, we probably have the best category. I mean, it's going to be very, very likely enough that we can focus our time on trying to get to that particular complexity in our technical or in our contest if we need to. But again, in computing contests, if you're doing ICPC, USCO, or something similar, if your brute force solution works, you take that, right? You take that, and you might want to start with that just to see if it will pass, okay? So for example, if I'm looking at this one and I'm thinking n fourth is terrible, but they're telling me it's going to be 50 on n, which means I'm only going up to 6.25 times 10 to the 6, roughly. Yeah, I'm definitely going to start with that solution, which is exactly what we're going to program as a part of this right here. So in terms of programming that solution, the description of this solution is pretty straightforward. If we want to come up with a better mathematical description of this, all we effectively just have to say is assume for a second that there is some function out there where this function will take I and j, and then it will compute a cost associated with that particular I and j. Our job is to minimize this function, okay? Minimize this function. And description of this function given I and j is effectively going to be the sum. And I'm just going to put real quick, it's going to be the sum here. I'm going to label these as I0, J0. It is going to be for all I, j, where I not equal to I0 or j not equal to J0. And we're effectively just going to compute that distance. So now we're going to have I minus I0. Sorry, these should be absolute values, plus j minus J0. These should be absolute values. And then we're just going to multiply this now by Gij based on what they gave us in the problem description. And so that's the weight associated with this particular cell. And that's effectively the mathematical description of what we're doing. And it should be clear from here where our complexities come in and what we need to do as a part of our solution. We need to hold a matrix that would associate the Gijs. Almost sounds like Gijs. But we need a matrix to store the Gijs, which we're going to get from our inputs. We're going to need a loop here. That's a nested for loop because it's for ij, so that's our n squared. And then since we need to minimize over all ij, we're going to have a for nested for loop, which just sounds disgusting to say. It's not really the business that we should be in, but that's where we find ourselves. And like I said, if brute force works, we take those. So let's jump over here into our terminal and start actually working on programming this solution. Okay. Boom. Okay, so here we are. We're in Algo Al's in the Rusty Solutions, and the first thing we need to go ahead and do is just get our solution set up. So I'm going to go ahead and copy this template from Hello RS into source solutions, ICPC Southeast Regional, and we're going to call this one restaurant opening .rs. Wait, hold on. Opening. Am I spelling that right? I'm getting self-conscious. Okay, spelling that right. RS. There we go. And now we can go ahead and open up our directory, find our mod file. And then now we just need a pub mod restaurant opening, which should be fine there. That looks good. And let's go ahead. Oop, no, I don't undo that real quick. Let's go ahead and copy that. Come down here, paste that in. And then now we're just going to pipe that into ICPC Southeast Regional. And then the restaurant opening. Oop, I don't know why I did it that way. Restaurant opening. There we go. And turbo that into main. Perfect. Already getting a little bit nervous. Don't know why I get nervous when I'm coding. Okay. Let's open up restaurant opening. Let's start talking about how we can actually solve for this particular problem. So based on our inputs, right? So if we come back over to restaurant opening, based on our inputs, we're going to be given a single line with n and m followed by n lines with m columns. So that means we're going to have a tuple here. Let n m be equal to this expression. We're going to have let mute buffer, set up our string builder to take in our inputs, IO to get the standard in. So then we've got standard in to take in that standard in, read line, and then we're going to pass an immutable reference to that buffer to read in all that data. This returns a result, so we'll unwrap that just to throw that IO exception if we have one. Afterwards, we now have that line, so we can go ahead and collect our parameters, which is going to be a vec over I32s here, and that's going to be set up on our buffer. We need to trim off the new line character. We need to then split on space, which produces an iterator. We need to map each element, so each parameter, and then we'll say s.parse turbofish into I32 and then unwrap the results. We actually get that 32, then collect them into our parameters vector, and then we can go and return that as a tuple. So now we can say params 0, params 1, and we can return all of that. So now we've got in and m, and then we need to go through in lines and m columns. So we're going to say for I in 0 to in as usize, because when indexing, Rust does prefer that the indexing variable be a usize, since the usize is based on your architecture, and it must be unsigned, so it can't be negative, so we don't get any out of bounds by going negative. Then we say for j in 0 to m as usize. Oop. Okay, let's go ahead and fix that real quick. Nice. And what we're going to be doing is we're going to be reading all these values in, and since they're all coming in off of a single line, one of the things I can do real quick is actually just take this logic and set up my x's, let's just call it, right? Or g's. Maybe g's would be a good way to call it here. So we can set up our g's, which is just a vector of I32s, and we can go ahead and paste in this code that we're using before to go and do the exact same solution, where our g's, which is that line, will be a new buffer. We read it in, we trim it, we split it, we map it, we collect it. And then what we're going to do here now is I'm just going to go ahead and return this collection, so that way we actually get our g's as that particular vector. And then what we'd be able to do now is to iterate over those to get their values. And so before we go into that, I can go ahead and say let mute grid now be equal to, and then if we want to set up one row of this grid, that would be all zeros, and we'll have 50 of them. And then to have a 2D matrix, we just basically add another square bracket around that and then say 50. So this is a row of 50 columns, okay? And there's essentially 50 rows is the way to look at this. And rather than allocating this on the heap given in and m, so that way it would be perfectly sized, since it's relatively small, only 2,500 cells, we can just statically allocate this grid here. And that's much more efficient for us, since this will be written into the memory of our program. And then now we can just say grid ij is equal to the g's at j, right? And now we've loaded up all of the data into our grid. So then now that we've got all the data loaded into our grid, then we can actually start iterating over that grid to actually produce our solution, which means that now we're going to have this for R1 in 0 to n. I'm going to go ahead and leave this one as an I32, because if I look back over here, I can see that the Manhattan distance formula uses the absolute value of a difference. And if we're using U sizes, we have to do this thing where we have to make sure that R1 is always bigger than R2. I don't really want to worry about that, so I'll just leave this as an I32 where negatives are permitted. So then we'll say for C1 in 0 to m, then we'll say for R2 in 0 to n, and for C2 in 0 to m. And that just does not look good. Okay, so the R1C1 means we're calculating the cost of associated with choosing R1C1 as the location, which means that we're going to have some let mute cost be equal to 0 here, and that's what we're going to calculate as we iterate over every other R2C2. And so then the way that this works with our cost now is we can just say cost plus equals, and then we can just do that formula. So that formula they provided was R1 minus R2, and then that's the absolute value, and then that's going to be added to C1 minus C2, and that's the absolute value as well. And then we just multiply that by our grid value, which is going to be associated with, in this particular case, R2 as U size, and then C2 as U size. Okay. So that's what we're working with so far. So again, our cost is going to be the Manhattan distance multiplied by the grid value that we have. Okay. And if R1C1 is equal to R2C2, then that distance will effectively go to 0. And I believe my face cam is probably blocking this right now. So let me go ahead and say let distance equal, and then we'll just go ahead and back this up so that way we can see this more clearly. And then we can say let, or sorry, not let, but cost plus equals distance times. There we go. Okay, so there's our distance calculation. And let's go ahead and properly format that. There we go. And so then we can do cost equals plus equals distance times the grid value. Okay, that's looking pretty good. Then afterwards, now we've computed the cost associated with R1C1, but we want to be able to maintain the minimum cost over time. So before we even enter these loops, we'll say let mute min distance be equal to, and I just want the biggest possible distance, so the way everything would be smaller. So I'll say I32 max. That's the largest possible I32. And then now down here, I can just say min, this should have been min cost, not min distance. So let's do 9K, okay, up real quick, min cost, there we go. And so we just want this to be equal to the CMP minimum of min cost and cost. And we don't currently have CMP, so we're gonna go and grab it, use standard CMP. And now we can go back to the bottom and we're looking pretty good there. So again, so here's what happens, right? We go through every R1C1 pair. That's a particular cell. That's where we're going to try to put our restaurant. Then we go through every R2C2 pair and calculate the cost, which is going to be distance by grid value, add all of that up, and then just see if we have a minimum. Afterwards, we just go ahead and say print line, and then we're just going to print off here our min cost, and that's going to operate as our solution. So, let's go over here. We don't need that. Thank you very much. And then we'll say control PW, open up a floating pane here. And then what I want to see is that I can actually run this and it will give me at least a few good samples. So we can say cargo run and then pass in our restaurant opening. Okay, that compiled pretty well. Let's look at our first sample here. Let's go ahead and paste that in. We got 7, which is what we expected. Let's look at our next sample. Paste that in. We got 591, which is what we expected. So this is already looking pretty good. The next thing I would normally do is go to the judging panel here to see the data. But when I checked it before, I didn't find restaurant opening listed here, interestingly enough. So I think they may have missed that one. So we won't actually have any test cases for this particular problem, but that's okay. The next thing that we should probably move to then is just actually uploading our solution to see if it works. Okay, and there we go. So we got 17 out of 17 passing. This solution has been accepted without any time limit exceed. So even though it's an end of the 4th solution, it works here just because the data size is so small. So anyway, so I hope that you enjoyed this episode and got something out of it. Let me know what you think in the comments down below. I'm really excited to be able to iterate onto this. I have what I think is a pretty cool solution for n squared here that I want to go ahead and give a shot. And then we'll be moving on to new problems as well, which I hope that you're excited for, because I certainly am. But until then, have a great night, and I'll see you in the next one.